Hello and welcome to my demonstration for my final year project, Visual Learner SLAM. I'll be sharing with you more on what Visual Learner SLAM does, and it's actually built for educational purposes. It does visual, simultaneous, localization and mapping. Visual Learner SLAM is also a graphical user interface GUI application that references the open source SLAM system OpSLAM2. This application provides real-time and simulated visual SLAM capabilities to help students, educators and researchers learn and experiment. Visual Learner SLAM is built on Qt framework, which allows for cross-platform development. Currently, it can be run on Windows operating system, Windows 8, 10, and 11. For Linux operating system, it has been tested on Ubuntu as well as Arch Linux. Here's the graphical user interface in real-time mode. It allows users to select and load the file, as well as choose the camera type, and as well as view the camera stream. It allows for customized learning, where users can select the feature detector and descriptor in the custom mode, and also allows for visual SLAM controls where users can initialize, start, stop and reset the SLAM system. There's also an option to enable local mapping. In the simulation mode, similarly, you can also load and select the files. Additionally, you can also select the type of camera as well as the simulation dataset like Kitty or Thumb. It also allows users to plot the saved trajectory where users can plot them for evaluation. Similarly, it also allows for customized learning and visual SLAM controls. Now let's dive right into the live demonstration. Here's the application running in real-time mode. So firstly, users will select the back of words vocabulary file. It is used to detect and match features in camera images. It contains a dictionary of visual words that represent typical patterns in the images. Once loaded, it will show a pop-up confirmation. Similarly, when users choose the camera configuration file, a pop-up will show and tell the users once it has been loaded. Users can select different camera sensors, monocular, stereo, as well as RGBD. Here I'm selecting the monocular camera and starting the camera stream. Here's me saying hi. Users can then select to start the OpSLAM2 system, and will show the output frame as well as the point cloud map. As we are running in monocular, you can see that it takes a while and it requires triangulation for it to work properly. So here's me trying to triangulate and bring in more points for the thing to map. Triangulation is used to estimate the 3D position of a point in the environment by using multiple 2D measurements of that point from different camera views. And here's how the point cloud map looks once it's plotted. The point cloud map is actually a 3D representation of the reconstructed map with the positions of the detected features in space. Now let's try to reset and see what happens. As you can see, it takes quite a while. Why is it hard for monocular cameras to identify these points? Well, triangulation is used to estimate the 3D position of a point in the environment by using multiple 2D measurements of that point from different camera views. It's done by estimating the depth of the point using the known intrinsic parameters of the camera and the disparity between the projection of the point in two different camera frames. So maybe let's switch to a different camera. I'm able to choose and select the camera, and a warning will pop up to ask me to make sure that I've connected my RealSense camera. RealSense cameras are actually depth sensing cameras developed by Intel to capture both RGB color and depth information. They're actually commonly used in various applications such as robotics, visual reality, 3D scanning, and AR. Therefore, we have actually integrated the RealSense cameras so that they can be used in our Visual SLAM system. As you can see, here's the plotted map. Oh no, I've selected the wrong camera configuration file. So why is it important? Well, the camera configuration file actually contains the intrinsic parameters of the camera, such as the focal length, principal point, and distortion coefficient. The Visual SLAM systems actually use this information to compute the camera pose and help to reconstruct the 3D map. Well, fret not. Visual Learner SLAM actually allows users to select and load this file easily, and now we're able to plot it properly. The Visual SLAM controls are useful because they allow the users to easily reconfigure the SLAM system. For example, users can actually use this control to restart a simulation and test them with different feature detectors and descriptors. I can then choose to reset or stop the SLAM. Now let's run this in simulation mode. You will similarly load up the vocabulary file as well as camera configuration file. You can then proceed to select the type of sensor. Simulations are run by loading a pre-recorded video sequences from a dataset such as Thumb or Kitty. This is used to simulate camera motion as well as obtain ground truth trajectory. Once loaded, you inform the users, and you can then start the SLAM process. Here's how it looks like when it's plotted out on the point cloud. as well as the points on the output frame. Previously, to start a simulation, users have to compile an executable file for the specific evaluation dataset and have to type it out manually. The user study we conducted actually identified these pain points, such as encountering compilation issues and having them to have extensive knowledge, thus making the Visual SLAM system out of reach to novice users. Now, you can choose to stop or reset the system. This gives users control and able to restart the simulation if they like to. Now let's see how it looks like when we're running a different simulation dataset. Let's choose the RGBD TARM dataset. The RGBD TARM dataset provides separate color and depth image sequences. The association file is used to align these sequences by specifying which depth image corresponds to each color image. This is necessary for accurate depth estimation and 3D reconstruction in a Visual SLAM system. Once initialized, you'll be able to see an output frame of how it runs with a RGBD sensor. The TARM and Kitty datasets are commonly used to benchmark datasets in robotics and computer vision research. They actually contain pre-recorded sequences of camera images, such as ground truth data and the 3D point clouds. Thus, it can be used to evaluate the performance of different algorithms. Thank you for watching my video's demonstration, and I hope you learn more about Visual SLAM.